Hi, George Diamond here. We're finishing up our flipped classroom unit. We're looking at limits and continuity, and this is the last section in our unit. Now we're looking at, today we'll be looking at, in our textbook, this is section 1.5, infinite limits. Now a couple of essential questions. Let's take a look at our two essential questions. Our first one, okay, what are infinite limits, and how can I recognize them? So what is an infinite limit? How do we recognize it? Also, what are vertical asymptotes, and how can they be identified? So what are vertical asymptotes? How can we identify those, right? So to get started, okay, with infinite limits. Okay, first, this is an infinite limit is simply nothing more than a limit in which f of x increases or decreases without bound as x approaches c. So a limit at which f of x increases or decreases without bound, so you have a vertical asymptote, okay? So as you look at the limit as x approaches c, from the right, I guess, would be positive infinity. As x approaches c, your function would be negative infinity. So as x approaches c, the limit as x approaches c of the function f of x will be positive infinity or negative infinity. So what we get here are some infinity and negative infinity for limits as you look at some of these asymptotes. Now, I put a little note here on a PowerPoint to kind of remind everybody that an infinite limit is technically not really a limit. It does not mean that the limit exists, all right? So just remember, the left-hand limit and the right-hand limit have to be equal to each other, right, before we have an actual limit. So an infinite limit or a limit at negative infinity or positive infinity technically doesn't exist. So as you look at the next slide on our PowerPoint here, it says it simply tells you how the limit fails to exist by indicating the unbounded behavior as x approaches c. All right, so that's all it does. So we say we have that the limit is negative infinity or the limit is positive infinity. That doesn't mean there's a limit. That just simply indicates the unbounded behavior of the graph. All right, so to get started, let's look at a little example. So find the limit of each function as x approaches 1. So we're going to run through a couple of these. All right, so you can kind of see the graph. Okay, we'll start off with this problem right here. So problem A, f of x equals 1 over x minus 1. All right, now to get the limit as x approaches 1, we take the left-hand limit and the right-hand limit. Now if you look at the graph on this, you got a vertical asymptote at x equals negative 1. So this would be, or x equals positive 1, sorry. So this would be our vertical asymptote here. All right, and looking at the graph looks like this. So this is the typical. And as you calculate the limit, so we do the limit from the left-hand direction and the limit from the right-hand direction. All right, so let's do the limit as x approaches negative 1 first. So the limit as x approaches negative 1, so this is a left-hand limit. That means we're approaching, so as x approaches 1 from the left, so you can imagine again as you look at your graph over here, and as x approaches 1 from the left-hand direction, you can see that y goes down, keeps going down further and further and further, so y basically goes to infinity, in this case negative infinity, all right? So as you approach the asymptote from the left-hand direction, the y value increases without, or decreases without bounds, so it goes to negative infinity here, all right? Now let's do the limit from the right-hand direction now. So we do so this is so we say the limit as x approaches 1, or 1 from the left-hand direction is negative infinity. Now once again, that kind of describes the behavior of the graph. And as you look at the graph, as x approaches 1 from the right-hand direction, so you can see coming this direction, as x approaches the vertical asymptote from the right-hand direction, y goes to positive infinity. All right, so we say that the right-hand limit as x approaches 1 is going to be, here it is, positive infinity. All right, so we kind of saw it just a moment ago. Okay, let's try a second example now. So once again, you just got this on my PowerPoint. And here's the next one. Let's try 1 over x minus 1 quantity squared. Okay, first, let's take a look at the graph. All right, so once again, we have a vertical asymptote at 1, so x equals 1. Here's our vertical asymptote. Now, the graph of x minus 1 quantity squared looks like this. All right, so let's do the left-hand limit and the right-hand limit. So these are simple to do, especially if you're looking at the graph like we are. All right, so to start, okay, let's do the left-hand limit first. So the limit as x approaches positive 1 from the left-hand direction. Right? So as you approach 1, as you approach, as x approaches positive 1 from the left-hand direction, you can see the y value goes to positive infinity. All right, so we say the limit as x approaches 1 from the left is positive infinity. Now, let's do the limit as x approaches 1 from the right-hand direction. Now, coming from the right-hand direction, coming from this direction, once again, you see the y value goes to positive infinity, right, again. So the limit as x approaches 1 from the right is positive infinity. So we can say the left-hand limit is positive infinity, the right-hand limit is positive infinity. Let's try another one. So find the limit. Once again, we're looking for the limit as x approaches 1. Get us to negative 1 over x minus 1. All right, so you look at this graph. Now, once again, we have a vertical asymptote at positive 1. Let's put our vertical asymptote in. And let's take a look at our graph. Now, the graph on this will looks like this. Now, this is just a PowerPoint graph. If you do it on your calculator, it'll look, very similar to this, but maybe a little bit different. Now, let's do the left-hand limit first as x approaches 1. So the limit as x approaches 1 from the left. And you see coming from the left-hand direction, y goes to positive infinity. So once again, the limit as x approaches 1 from the left is positive infinity. Now, the limit as x approaches 1 from the right, and you can see as we approach 1 from the right-hand direction, the y value goes to negative infinity. So we say in this case, the limit as x approaches 1 from the right-hand direction is going to be negative infinity. All right. Let's try another one here. So we have one more. Okay, let's do f of x equals negative 1 over x minus 1 quantity squared. So let's try this here. Now, let's take a look at our graph. All right, so let's take a look at our graph. Now, once again, we have a vertical asymptote at x equal 1. All right, so let's go put our asymptote in. And the graph this time looks like this. Right, so negative 1, remember positive 1 over x minus 1. This is reflected over the x-axis kind of. So as you look at our limit now, let's do the left-hand limit first as we look at our left-hand limit. So the as x approaches positive 1 from the left-hand direction now. Right, so coming from the left-hand direction, again, y goes to negative infinity. So we say in this case, the limit as x approaches 1 from the left is negative infinity. And once again, as x approaches 1 from the right-hand direction, y goes to negative infinity again. So we say the right-hand limit as x approaches 1 is negative infinity also. Right, so you can see negative infinity. Okay, let's take a look at some vertical asymptotes next. All right, so let's take a look at some vertical asymptotes. First, let's define what a vertical asymptote is. It says if f of x approaches infinity or negative infinity as x approaches c. So if you have an infinite limit, okay, from the right or left, then the line x equals c is your vertical asymptote. So as x approaches, f of x approaches infinity or negative infinity as x approaches some number, from the left or the right, okay, then the line x equals c is going to be our vertical asymptote, right? So our vertical line is always x equals some number, right? So it'll be x equal that number, and that'll be our vertical asymptote. Now let's look at a couple of them here. So this is a couple examples. Find the vertical asymptotes of each graph. So let's start off with this first example here. Now, once again, just remember now, when you're getting vertical asymptotes, all you're really doing, you're simply finding the zeros of the denominator. Right? So that's all you got to do. If it's a rational function, if you got asymptotes, okay, you just have to find the zeros of the denominator pretty much. So, to get started, okay, let's do f of x equals 1 over 2x plus 2. Right, so let's see if we can get the vertical asymptotes. Just a simple rational function. So to get started, the denominator 2x plus 2, let's take the denominator, set it equal to 0. Solve this for x. We get 2x equals negative 2, or x equals negative 1. X equal negative 1 will be our vertical asymptote. Right? Now if you look at the vertical asymptote, it'll be right here. And this is what the graph will look like. Right? But the vertical asymptote will be x equal negative 1. And when you have a fraction like this, remember, you're going to let the denominator of the fraction equal 0. And then you got to find the zeros of the denominators. Right? Okay, let's try another one. Now, our next example. Okay, here we go. This time let's try y equals x squared plus 1 over x squared minus 1. So let's try this right here. Now, once again, let's take our denominator, let's set it equal to 0. So let's do x squared minus 1. Set this equal to 0. Now you got to solve this for x. So you know with x. Now I'll solve this by factoring it. X squared minus 1 is the difference of two squares. This one factors x plus 1 times x minus 1 equals 0. So you can solve it by moving the negative 1 over and then taking the square root. That will give us our two answers also. We have x plus 1 times the quantity x minus 1 equals 0. So our solution then will be negative 1, x equal negative 1 or x equal positive 1. So this particular problem now, you've got two vertical asymptotes. All right, so we've got two. So if you look at our graph, so you got a vertical asymptote at negative 1, vertical asymptote at positive 1, and it looked like this right here. All right, so a negative 1 and positive 1. And the graph now will look sort of like this right here. So this is kind of a, you can see the two asymptotes there. It'll look like this right here. So let's see, let's try another one. Let's take some properties. We'll do some properties on limits next. All right, let's try, let's see, now once again, to begin with, when we look at our properties now, let's describe two functions here, or two functions. You got f of x and g of x. Now, describing our two functions and the limits of each. So you get the limit as x approaches c of the first function, f of x. Now that's equal to positive infinity, right? And let's let the second function, the limit as x approaches the same number, g of x equal some number, L. All right, so whatever the limit would be. So this one has an actual limit. Okay, this one has an infinite limit, either positive infinity. So we're kind of describing our two graphs. You got f of x and g of x. Okay, f of x, the limit as x approaches that number is infinity, and for g of x, as x approaches that number, as x approaches c, the limit actually does exist. So this is the limit that's going to be L. All right. Now, the first property we want to look at here is what's called the sum difference property. All right, so if you have like a polynomial or something like this, so you get the limit as x approaches c of f of x plus g of x. All right, so the limit as x approaches c, f of x plus g of x. Now, we said the limit of f of x is going to be infinity. The limit of g of x is going to be some number. Well, infinity plus some number gives you infinity. All right, so so infinity plus some number gives you infinity. Okay, let's look at our next property. Okay, this is called the product property. Now, the product property, you've got, once again, if you take f of x and g of x and multiply them together, right, so the product of two functions, and the limit as x approaches c. Now, once again, remember, the limit of f of x is infinity. The limit of g of x is some number, all right? So infinity plus some number gives you infinity, if L is greater than 0. So if the limit of g of x is a positive number, you're going to get positive infinity. Now, if the limit of g of x is a negative number, like so the limit as x approaches c of f of x times g of x. Now, if the limit of g of x is a negative number, so if the limit is less than 0, you'd have infinity times a negative number gives you negative infinity. All right, so the limit here, to describe the limit, would be negative infinity. Let's see, our quotient property. Let's take a look at that also. So the quotient property. So we take the limit as x approaches 0 of g of x divided by f of x. So g of x divided by f of x. Now we said the limit of f of x was infinity, g of x is some number. All right. And let's see. There you go. So once again, the limit of g of x is some number. Let's say that f of x is infinity. Right? So you get some limit divided by infinity, which is 0. Right? So you can imagine if the denominator of a fraction, as the denominator of a fraction gets bigger and bigger and bigger, you've got this number divided by you can imagine numbers that increase in size. The fraction itself goes to 0. So the bottom of the fraction gets larger and larger and larger. Okay, the fraction itself will approach 0, so it goes to 0. Okay, let's do a couple examples. Let's see if we can find this first limit here. Let's do the limit as x approaches 0 of 1 plus 1 over x squared. All right, so the limit as x approaches 0 of 1 plus 1 over x squared. Now, to begin with, as x approaches 0 of 1 over x squared, now 1 over x squared, the limit here would be infinity. So what you end up with is 1 plus infinity. And remember, any number plus infinity is still infinity. So we describe this limit here as x approaches 0 as just infinity. All right? And once again, 1 over x squared would be infinity. Okay, what about this here? Let's try some trig function now. All right, take a look at this one. So we got the limit as x approaches 0 from the right-hand direction of 3 times cotangent x. Now, let's break this apart as 2 separate limits. We'll do the limit as x approaches 0 from the right of 3. The limit times the limit of cotangent x as x approaches 0 from the right. And now the limit of cotangent x as x approaches 0 is infinity. You end up at 3 times infinity, once again, which is just infinity. So once again, it's another infinite limit. But the first limit exists. This is 3 times whatever the limit of the second function is infinity. 3 times infinity is infinity. Now, so we have another example now. Let's look at this one here. So we take the limit as x approaches 1 from the left. So the limit as x approaches 1 from the left. Now, what I'm going to do, so every time you do a limit, let's try direct substitution first. Let's take the 1, plug it into our function. Now remember, if you get 0 over 0, 0 over 0 indicates a hole, right? So it is possible that we can run into a hole here. Let's substitute the 1 in. It gives us 1 cubed minus 1 over 1 squared plus 1 plus 1. Now 1 cubed minus 1 gives you 0 over. Now in the denominator though, we've got what? 1 squared plus 1 gives us what? 3. So it'd be 0 divided by 3, which is 0. So this particular limit here, by just using direct substitution, gives us 0. We did not get 0 over 0, so there's not a hole there. Right? So the actual limit here would be 0. And now we'll have a part 2 of this video lesson, so look for the second part, and we'll be actually just solving some more problems, finding some more asymptotes, and that type of thing with the second video. So that'll end this video, and we'll do the next video in a second.